Hi, my name is Behnaz Arzani, and today I'm going to be talking about our solution for interpretable feedback for AutoML systems. So the reason we started working on this problem was because we observed that machine learning is often not accessible for network operators and domain experts. And if you look at some of the work that our community has done for using machine learning to improve data center operations, you see that a lot of times there's this need to collaborate with network operators and domain experts. So because domain customization actually improves the accuracies of these models by a lot. So some examples of these are work such as Napuro, which helps do diagnosis, Pensieve, that is used for video delivery, Resource Central, that predicts the resource requirements of VMs to do better VM placement, Private Eye, that does compromise detection within a data center network, and Scouts, that does incident routing to improve incident mitigations in the cloud. And if you look at each of these machine learning models, while they provide meaningful benefits in practice, they're often domain customized so that they can scale and achieve high accuracy. And this is why if network operators want to employ machine learning, they often need to collaborate with data scientists so that they can provide the domain knowledge and the data scientists can provide the ML expertise so that they can come up with an effective model. So what the solution often looks like is that network operators provide the data, they provide some context about the problem and about the data. The data scientists take that information, create a machine learning model, and they iterate on this because often the first iteration is not accurate enough or not scalable enough for the operator's needs until they converge at a solution that's deployable in practice. And as you can imagine, this process is often inefficient and slow, and it's also expensive, especially when we're trying to test for viability. So the machine learning community, observing this, not just in networking, but also in other domains, have created AutoML systems to try to automate the job of this data scientist and enable domain experts to try machine learning models on their own initially to try to see if that is the right solution for the problems they have. And so what some of these AutoML systems do is that they search over possible models and their hyperparameters, for example, decision trees, support vector machines or perceptrons, random forests, k-nearest neighbors, Gaussian processes. And then from these, some of these AutoML systems would come up with an ensemble of machine learning models. And some examples of AutoML systems that operate this way are TPOD and AutoScikit-learn. And they produce this ensemble of ML models to the user, which in our case would be the network operator or the data center operator. So let's look at what this replacement solution would look like. So instead of having data scientists, the network operators are now providing data to the AutoML system. But they've lost one important factor. They're no longer able to input domain knowledge into the AutoML system. And so they've lost this ability to use what they know about the problem as part of the solution. And that's a huge, huge loss. Especially if you look at some of the earlier systems we talked about and how domain knowledge has helped improve their scalability and accuracy. The other problem we run into when we go into this domain is it's hard to identify how to improve accuracy when you put in the data into the AutoML system and it fails to produce a model that's accurate enough. And this is why we started our research on bridging the gap between AutoML systems and network engineers. And we identified two possible ways of going about this work. The first is creating means of allowing operators to input their domain knowledge and compiling that into information that the AutoML system can automatically incorporate. For example, some examples of that might include how do you get priors about the problem from a network operator? And some models actually allow you to encode priors, and so you can use that as part of improving the performance of AutoML. The other avenue of improving AutoML systems and allowing the network operators to leverage them better is to provide interpretable feedback. Now, we'll focus in this talk on the second aspect, on how we provide interpretable feedback for network operators when using AutoML systems. So the solution we create is going to be based on two concepts. The first is ALE plots, and ALE plots are a means for interpreting the output of individual models. So basically, they allow you to learn or understand what an individual black box machine learning model has learned about a particular problem. Now, our idea was to combine this interpretability technique with a technique from active learning where a QBC algorithm, a query by committee algorithm, would tell the user, add this new data point to your training set to improve the accuracy of your machine learning model. So what query by committee does is, given an input, it scores that input in terms of how useful it's going to be for improving the accuracy of the machine learning model. But because we don't have time, we're not going to go into the background of exactly how these algorithms work, but instead are going to focus on the intuition behind our solution. So the intuition of our solution is the following. We aim to interpret individual models within the AutoML ensemble. Remember, when you look at AutoScikit-Learn or TPOT, what they're doing is they're doing a search over traditional machine learning models, and then they return a set of these machine learning models, an ensemble of these machine learning models that collectively give you a model with high accuracy. So what we can do is we look at each of these components of this ensemble, interpret what they have learned, and use the disagreements across these machine learning models to provide feedback to the operator. So again, this would mean we use a model agnostic interpretation method, in this case ALE, to see what each model in the AutoML ensemble has learned about a given feature. And then we use the disagreements across these models as an indicator for more data, where more data is needed. So to get the intuition about why this approach works, take this toy example where we have a collection of cats and rabbits that we want to label as cats or rabbits, and this is what our machine learning task is. We want to separate cats from rabbits. And we have pictures ranging from different ear sizes in both cats and rabbit that is going to be input to our AutoML system, in this case AutoScikit-Learn. So then, let's say that we are now doing this understanding of what each model has learned, and what we find is that the random forest has learned that if the ears of the animal is 3 inches, then we have a rabbit. The perceptron has learned that if the ears are 3 inches, then it's a cat. And the random forest has learned that if the ears are 3 inches, then it's a cat. So we see that these models are disagreeing on what 3-inch ears indicate. And what we can use this disagreement on is to see, okay, what did I see in my training data that caused me to make this mistake or have this disagreement? And what we find is we actually had 2 rabbits with relatively short ears, and that is why these machine learning models got confused in terms of, well, does short ears mean cats or does it mean rabbits? And so the solution intuitively is that you might want to increase the number of rabbits you have with short ears, or increase the number of cats you have with different ear sizes, so that you can improve the accuracy of your AutoML. So let's look at a real example in the context of a DDoS detection algorithm. Now here, an operator might use our solution and look at the ALE plots for the source port feature. Now, one thing that I want to point out here is we're already providing one piece of benefit, which is we're looking at what the AutoML system has learned about individual features separately, which improve interpretability. But beyond that, he sees that there's disagreement across the machine learning models in the ensemble in the range of 0 and 40,000, right? And not knowing context, one might think, well, I need more data that has that source port in that range so that I can reduce this confusion. But the operator, knowing that the source ports are usually assigned at random, will decide that it's not necessarily worth it to add data with source ports in that range. Instead, they might look at what's happening on the destination port and see that there's disagreement on whether we have DDoS traffic when the destination port is 443. Knowing that this is HTTPS traffic, they would know this is a common target for DDoS attacks, and then they might decide, okay, it's worth adding more data with the destination port 443. It's as simple as that. And so in conclusion, we've created this solution that allows us to interpret the output of AutoML systems and identify data points that we can add to the training set to improve the accuracy of these AutoML systems. And what we're proposing is to get the full benefit that AutoML systems can provide, we need to domain customize these AutoML systems to allow operators to input priors and domain knowledge about the problem into the AutoML system. And this is an area we think the community can contribute to a lot. And finally, we've provided an interpretable feedback solution that creates one component of this larger idea of an interpretable, domain customizable AutoML system for networking. And with that, I'm happy to take questions. Thank you.